Hi, in this video we are going to look at the identification and treatment of univariate outliers. So we will of course start with the identification of them, but it's good to know what we intend to do once we've identified them, i.e. the treatment. And typically people will treat outliers in one of three ways, sometimes even a combination, and they will do their analysis depending on multiple times using different approaches to treating outliers and seeing if there's a particular impact. But the first approach to treating with outliers is simply to identify them, state that they are there, and continue with the analysis with them included. Some people, the kind of argument for them is that outliers are legitimate parts of the data set. The argument against doing this is that there are particular statistical models where the assumption is that there are no outliers in the data, because outliers can greatly skew or impact a model. The next approach that people do as the opposite is to remove outliers. So the data set that you'd be working with is a bit smaller, but it doesn't have any statistical outliers within it. So you identify them, and then any data point that's an outlier gets removed. And the third approach would be to transform the outliers. Often that transformation is from being an outlier to the value that is the limits of which beyond those limits are outliers. So to give an example, let's say you were identifying outliers based on a number of standard deviations away from the mean. There's many ways, and I'll talk about the different approaches that people use to identify in a minute, but if we just take that one, let's say that the rule that was going to be used was 2 standard deviations either side of the mean. Anything beyond that is considered a univariate outlier. Well, if we have a mean of 50 and a standard deviation of 5, 2 standard deviations equals 10, and then 10 either side of the mean, for 2 standard deviations either side of the mean, means any data point that is below 40 or above 60 is considered a univariate outlier. If you had a data point of 65 or 62 or anything above 60, in this case people might transform it to 60. Transform the univariate outlier to the upper and lower limits of which outliers are defined by. So there are the approaches. Obviously we don't need to go through if you're just treating outliers if you're just leaving them in the data set, but I will show how to remove outliers completely and how to transform them to a particular value, specifically the value as those limits. In terms of defining outliers then, there are 3 general approaches that people take to do so, and the first and probably the least robust and as such least common way is to take a specific number of standard deviations either side of the mean, like I just discussed. For example, 2, 3, 2.5 standard deviations from the mean. The implication of this is if you were to remove or transform your outliers, you could have a fairly significant effect on that mean value. So the more robust approach is a number of median absolute deviations or distance from the median. Because, for example, if you were to transform outliers, you're not going to change the median value. So some people will use 2, 2.5 or 3 median absolute deviations either side of the median. And then the most common way, it's described in the literature as being the most robust approach, is to take the interquartile range, which I'll demonstrate and visually show shortly, and multiply that value by 1.5 or another value, which again I'll also show you the different values that exist, and take that particular value and subtract it from the Q1 value, the quartile 1 value, or add it to the quartile 3 value, and there are your limits. So again, it's a distance from the median approach. So there are ways to identify them. That'll become a little bit more clear now as we go through actually doing this. The first thing I'll say is I'm going to do it with the iris dataset. So here's the iris dataset. We have 4 numeric variables and 1 group variable. For the purpose of this demonstration, I'm going to completely ignore the group variable of species and just pretend that we've got 4 numeric variables that we want to examine and identify to see whether there are univariate outliers. If this was your own project, you may want to do this within groups, but this is just a demonstration of the process as opposed to a discussion around a particular project, and we're not doing it with a particular agenda. So we'll work from there. So the first thing, I'm just going to give a heading of univariate outliers, and we'll start with detecting them. And I'm only going to use one method for detection, the 1.5 times the interquartile range subtracted from the quartile 1 value and added to the quartile 3 value. But the first thing I want to do is, because the box plot approach in ggplot is that formula. So I'll create the box plots, and then I'll speak a little bit more about that. So to create the box plots, we'll use ggplot. We want the iris data set, and our aesthetic mappings, the x-axis will be the numeric variables. So we have sepal length is our first one, and we want to create a box plot of this John box plot. If I run this, make this a bit bigger, but what we see is there's no outliers using this method of detection. There's no, and how they appear actually is as a black dot at the end of the whiskers. So there's none for sepal length. If we try all of them, so we've got sepal length, we've got sepal width, we have petal length, and we have petal width. If I go to sepal width, this is what outliers look like. So we have one outlier which is on the lower limits with a data point of 2. We have another outlier with 3 outliers, sorry, in the upper limits with values above 4. And just before we proceed, there are none on petal length, and there are also none on petal width using this method of detection. So we're gonna work with the sepal width variable specifically because this one has outliers. So what is the Q1 data, our quartile interquartile range? Well, it's 2 specific values. Our quartile 1 value, which is represented by this vertical line here, the beginning of our box, subtracted from the quartile 3 value, which is this value here. Now the quartile 1 value describes the value up to which 25% of our data are contained. So from 0% of our data to this value here, which looks to be about 2.8. So we can see 2.5 and 3, so that's 2.75, so it's probably 2.8. That's our Q1 value. On top of that, then we've got our Q3 value. So between none of our data up to this value contains 75% of our data, which looks to be about 3.3. So subtracting this 2.8 value from 3.3 gives us 0.5, which is our interquartile range. Excuse me. If I were to multiply 0.5 by 1.5, I'd get 0.75. And when I subtract that from Q1, so I subtract 0.75 from Q1, and I add 0.75 to Q3's value, I get my limits at which beyond are univariate outliers. So that's how univariate outliers are detected in this approach, and we'll do this manually. Okay, we know we're only working with sepal width here, So we're going to do it manually. If you were reporting, you could, writing an article at the moment, you could say that all variables were checked for univariate outliers using the box plot method, and the box plot method in this instance is 1.5 times the interquartile range minus subtracted from Q1 and added to Q3 values, and that identified four specific univariate outliers. We can actually see which cases those are as well if we go into our data set. We know it's the lowest one on sepal width, so case number 61 has a sepal width value of 2, which is exactly what we can see. So we know case number 61 is a univariate outlier. We also know our highest most values in sepal width, 4.4, which is this one here, 4.2 and 4.1 are all above 4, and they are also univariate outliers. But we want to write reproducible code that shows how we establish them and that shows how we're going to treat them. So the first thing is let's do this somewhat manually. We can use the quartile, not the quartile, it's quartiles we want. We can use the quantile method to establish this. What are these values? So we've got iris data set, and it's the sepal width variable. Let's just run this code just for a moment. If we do that, we can see our Q1 value is 2.8 and our Q3 value is 3.3. If we just want, which is what we actually want, is only to extract the Q1 and Q3 values separately, and I'll show you why in a moment, we can use the probs function. And we looked at this previously on the descriptive statistics section of this video series. So probs of 0.25 will give us just the lowest value. You can see there 2.8. And equally so, probs of 0.75 will give us just the highest value. Now we want to calculate our interquartile range, which is the higher value, the Q3 value, subtracting the lower value. First of all, we're going to have to save these to our environment so we can use them in establishing the interquartile range. So it's going to be sepal width Q1 will be our first one. Sepal width Q3 will be our second one, and this is now going to save into our environment. So I'll run both lines. I'll run them separately just to show you them. Q1 is now 2.8. Q3 is 3.3. We can now, if we want to get sepal width interquartile range, so IQR, we can subtract sepal width Q3 minus sepal width Q1, and that will give us our interquartile range, 0.5. Alternatively, and this is just a demonstration, sepal width IQR.2, there is an IQR function, and we would do that on the iris data set and specifically the sepal width value. And when we do this, sepal width IQR2, just an additional way, that also comes in as 0.5. So we could have immediately got the IQR that way. However, we do actually want the Q1 and Q3 values. I'll leave this line of code there. But if we want the IQR value, the 1.5 times the IQR value, so sepal width IQR 1.5, it would be sepal width IQR times 1.5. This should give us a value of 0.75, which you can see here, sepal width IQR 1.5, it does. So I should actually probably just delete the 0.2 one because it's a little bit confusing. Now I will remove it, remove sepal width IQ, so remove to remove it from the environment. So now that's gone. And we can then take our Q1 value and subtract the sepal width IQR 0.5 and take the Q3 value and add it. So we'll say sepal width uni sepal width uni outliers lower is going to be Q1 sepal width dot Q1 minus our 1.5 times the interquartile range, which is this. You can see here it's 2.05. 2.05 is somewhere here, and that's our boundary for our lower limit of univariate outliers. If we want the higher ones, so we'll say high, it's the Q3 value plus rather than minus, because we're moving in the upper direction away from the median, the 1.5 times the IQR. And this gives us a value of 4.05. So we did a fairly significant amount of work in order to come to these two values, these two exact values, which are our limits. Now, the transform approach, so the remove approach would be to delete anything that was beyond those values, and the transform approach would be to transform the individual data points to those values. This is quite laborious. I'll get rid of these lines. We've wrote 6 lines of code, and this is only to identify outliers in a one variable. We would have to do this, depending on the number of variables you have and depending on the number of outliers, this could become quite a lot. So there is a package, and the package is to deal with univariate outliers. If we go to library, univariate outlier or univ_outl package for the detection. So specifically the detection of univariate outliers. I go to my packages and just show you what the package looks like. The function is boxb, box plot based outlier detection, which is what we've actually been doing. We've just been writing the code up to now. So we're going to press enter a few times to move this up a little bit. What we do, x is the variable that we're going to use. So a numeric vector. So we'll start with that, boxb. First thing is x equals, and it's the iris data set, but specifically the sepal width variable. Next, k is you can see the common values here, 1.5, 2, and 3, and that is the multiplier to the interquartile range. So k is going to equal 1.5, because that's what we've used. You can see it here in line 253. It's 1.5 times the interquartile range. And then we've got our method. Resistant is your standard box plot fences, which is exactly what we did. Method equals, and we want to include resistant. Okay. There are other methods, and if you scroll down you can learn about them. So it's Q1, so method equals resistant, Q1 minus k, which we've set at 1.5, times the interquartile range. The asymmetric one is 2 times k, and the ADJ box, the citation is given for it here, which is based on, both of those are based on how skewed your data is 1.5 times the exponential of a times m QR, and it goes into whether you've got positive or negative skewness, and all the details are there for that. but we're going to go with the standard one. And just to check that it is actually meant to be resistant, it is. So if I run this now, you can also check for IDs if you have a specific ID one, but we're just going to use the row number here, exclude particular values and do the log transformation. So if I run this code, and here we get exactly what we've previously calculated. Quartiles, fences, lower and upper, excluding none of them, and our outliers 16, 33, 34 and 61. So it tells us our outliers, which is really, really convenient. Rather than doing all of this, we could just use one line of code. And more than that, we can save that as well. So if I was to just do, I'll save it as, so sepal width, and I'm going to save it as uni out for univariate outliers. I'll save that, and it says, look, the number of outliers on the left tail is 1, number on the right tail is 3. Still just one line of code. And specifically, if I open this now, sw uni out, we can see we've got quartiles, we've got fences, those that are excluded, the 4 values. It gives everything in that one line. And we could do that 4 times, and that would do it for all 4 variables rather than having 6 lines for each. What it gives us is really nice. It gives us sw uni out. And within this, we've got fences and lower and upper. Fences is like our variable, just like we've done here, the data set and then the variable. So fences. And within fences, you have lower and upper. So that's a particular data frame. So here's lower. This is just calling a particular value. You can see now how it's appeared in my console. I'm just going to, and I'll do the same for upper. And this is actually not something that you need to type right now, but it's handy just so you can see what we're calling to when we write this particular line of code. So now we want to deal with our outliers. We're going to use the sepal width. We're going to use sepal width variable. I can call back to, I'll clear my console. I can call back to my box plot. Okay. So here's my box plot. We know there's 1 and 3 on the other side. We know what our values are by these 2 particular lines of code, which is anything less than 2.05 and anything above 4.05. Now before I'm going to treat anything, I want to work in a data set separate to my iris data set. I'm going to call it iris.uni out. So iris univariate outliers. And I'm going to make an exact replica of the iris dataset. So all of this is still perfectly acceptable. I'm just making a replica. So now from now on, I'm just going to work and kind of play around with the iris uni out dataset rather than my iris dataset, which I'm keeping intact. It's very handy. You can duplicate datasets to work with and adjust without harming, so to speak, your core dataset. The first thing I'm going to do is I'm going to make a new variable within this. So iris uni out, and we've already got this, and I'm going to call the new variable sepal width dot out dot sepal width outliers removed. Okay, that's what I'm going to call it. And I'm going to essentially duplicate the variable first. So I'm going to create it by making it identical to our iris uni out one and sepal width. So here's what happens. So before I run the code, here's iris uni out. Run this code. Now iris uni out has 6 variables. I have duplicated the sepal width variable just over here. Now I can actually mess around with this variable but keep my sepal width variable completely intact. So how do I remove them? Well, removing is relatively simple. And I remove it. So first of all, I want to take this data. Right, this is my this one. This is my new variable. I can do whatever I want to this. It's really not an issue. But I want to call to specific data points within it. And the ones that I want to call to within it are any that are greater than a particular value. So I'm going to take any that are within the sepal width value that I used before, but that are greater than the upper value. Now, I didn't have to write it here, it's just convenient for me to copy and paste. And I want to convert all of those to NA. NA will replace them all. So before I run this code, let's go back to our univariate outliers. We know that anything above on sepal width, so I'll sort by sepal width, anything above 4.05 is an outlier. So here are these. My code, which is take the iris uniat dataset, which is here, the univariate outliers removed dataset, which is this one. And then of the data within it, which is the square brackets, within that particular one, any value that is greater than the sepal width value, because they're identical at the moment, which is greater than that upper fence, goes to NA. And let's see, I've run that, I'll go back here, I'm going to order my sepal width again, and now they're NA, rather than being the value. So they are now removed. We now have, rather than 150 data points, we have 147. I've turned 3 of them to NA. I could equally, extend this, I'm going to take the exact same data set. Alright, these 3 are removed. We take the lower ones, you can see the 2 is still there, and now I'm going to do less than the lower one. Goes to NA. Run this line of code, and now the 2 is gone, but so too still is the upper ones. That's important. So we needed to do this line here first in order to create the data set to adjust. Otherwise it wouldn't have done anything, because it was putting NAs into a data that was already a series of NAs. How do we instead, so if we didn't want to remove them, perhaps we just want to transform them. I'll do the exact same process, but rather than removed, I'm going to do transformed. Alright, so I'm recreating another variable. I've added it here. It's identical to sepal width, so I'll sort by sepal width again. You can see NA here is the removed one. It's still there in the transformed one. On the upper end, 3 removed. The transformed is completely untouched. And now we will do iris univariate outliers transformed. Right, following the same approach here. Opener square brackets to talk to a specific amount of piece of data, which is now going to be anything. So we're going to take that, and again it's going to be, oh, I actually have copied all of that. Anything greater than the upper fence, rather than go to NA, let's change it to the upper fence. And I'll just, we know what I'm going to do next as well. I'm going to take all of that, put it here, Now anything less than the lower fence, we're going to change to the lower fence. I'll run both of these lines together because that's not a problem. So let's look at this. Here's our iris data set. The original data set is the first 5 columns. The removed one and the transformed one. I sort it here. Here's the original one, which was 2, which was an outlier. Outliers removed, it's NA. Transformed, it's been transformed to the lower limit. On the upper side, you've got a sepal width on its own. You've got the removed ones, and then you've got the transformed ones, which are now all 4.05. It's now very straightforward for me to, if I want, plot this again. So I'll go back to my sepal width box plot. So what am I going to do? Sepal width looks the same. Rather than sepal width, I'm going to take my sepal width outliers removed as my variable. Actually, I will just copy it fully twice. So sepal width outliers removed as my new variable. And the last one is sepal width outliers transformed. Not sure why nothing is showing up. Oh, because I'm not using the iris dataset. It's iris uni out dataset. I should have done this. So we've got our sepal width, which has our outliers. The removed outliers, there's no more outliers, they're gone. They've been deleted from the data, and you can see our warning. 4 rows contain non-finite values, they're gone. And the transformed ones, also no more outliers, but the 2 plots are ever so slightly different. And you can see the difference, and the difference is coming, you can see it more clearly at the upper end. When they're gone, our highest value is 4. When they're still in there, our highest value is 4.05. So 3 different approaches. Now we have a data set where all 3 approaches exist. We can conduct analyses using those different variables, see if the impact of outliers, see how significant the impact of outliers was. And you can also see that by using, obviously we didn't need to write these 2 lines of code here, but it was useful just to show them. We also didn't need to create the new, data set. I just wanted to keep the iris data set completely intact for future videos. But you can see how that box B function is really useful, makes it very convenient to treat outliers in whatever approach you would want to treat with. It really becomes more valuable in terms of the efficiency of the code that you're writing when you have more variables and more outliers to treat. But here, that's it. That's a video on identifying and treating univariate outliers.